Randomness and probability are very powerful and useful tools that we will be using all the time in statistics. When we gather our sample, we will gather our sample randomly from the population. And then if we're doing a controlled experiment, we'll randomly divide our sample into different groups, treatment and control groups, which means we're going to be using randomness and probability all the time. And fortunately, we know a lot about those things. Probability was figured out centuries ago by some really smart mathematicians, which means that we can learn this tool. So the first thing is probability is a number. We use this number to describe the likelihood of an event to happen. So a probability of 1 means we have a 100% chance an event will happen. It will definitely happen. A probability of 0 means that it's impossible. It's definitely not going to happen. And then all probabilities are fractions and decimals somewhere in this range. So a probability of 1/2, 50% would be the probability if you flip a coin, you'll get heads. If I roll an ordinary 6-sided die, well, the probability of rolling, say, a 5 is going to be 1/6. If I have an ordinary 52 card deck of cards, well, the probability that I draw any one card, say the 2 of hearts, well, that's going to be 1 out of 52. Important things to know are that no probabilities can be negative and no probabilities can be larger than 1. You never have more than a 100% chance that anything happens. So, what if I have multiple random events taking place? The first thing we need to consider are mutually exclusive events. The term mutually exclusive means you can't have both of these events happen. Either one happens or the other one happens, but never both. So like for instance, if I flip a coin, it's going to be heads or it's going to be tails. I can't get both heads and tails at a time. Or for instance, if I draw a card out of a deck, one single card, I could get the 2 of hearts, I could get the ace of spades. I'm never going to get both on the same card. That's ridiculous. That doesn't make sense. So if I want the probability that either one of the 2 events happens, either one makes me happy, and they're mutually exclusive, then I can just add up these probabilities. Like for instance, if I flip a coin, what's the probability that I'll get heads or tails? Well, there's a 50% chance of getting heads, 50% chance of getting tails. 1/2 plus 1/2 is 1, which is 100%. There's a 100% chance I'm going to get either heads or tails. Similarly, if I want to say, well, what's the chances that if I take a deck of 52 cards and I draw one card, I will get either a 2 of hearts or an ace of spades? Well, that's a 1 out of 52 for one of the cards, 1 out of 52 for the other one. That's a total of 2 out of 52, or a probability of 1 in 26 that I will either get this or that. Either one would make me happy. All right, this leads me to the addition rule. Suppose I have 2 events, event A or B, and I want to know, well, what's the probability that A or B happen, and what if they're not mutually exclusive? What if it's possible that one can happen and the other one can happen simultaneously? The mathematical formula for this is the probability of A or B equals the probability of A plus the probability of B minus the probability that they both happen, A and B, that they both happen simultaneously. Now, let's see what that means. All right, here's an example. I have a friend in Seattle who absolutely loves to work. So let's let event A be that he walks to work. Let's say that is 70%. He has a 70% chance on any given day that he's going to walk to work. Event B, on the other hand, is, well, it rains. He lives in Seattle. It rains a fair bit there. On about 40% of days it rains. So the probability of event B is 0.4. And also, usually he tries not to walk when it rains, but sometimes that happens. So sometimes he both walks and it rains on the same day, probability of A and B. Let's say that's about 20%. Suppose I ask you, well, what's the probability that either it rains or he walks to work? Well, notice that in this case, they're not mutually exclusive, so I can't add them up. It's not just 0.7 plus 0.4. That would give me 1.1, which is ridiculous. You can't have probabilities over 1. What went wrong? Well, there's a chance that both happen. That 70% and that 40% both include that 20% chance that he walks and it rains on the same day. So I need to subtract that out. That 20% is part of the 70%. That 20% is part of the 40%. So if I just add up the 70% plus 40%, I'm going to catch that 20% twice. Well, that doesn't make any sense. So I add up the 70% chance that he walks to work, the 40% chance that it rains, and then I subtract off the chance that both are going to happen, because that 20% is included in both the 70% and the 40%. I subtract that off, and therefore, based on this data, there is a 90% chance that either it rains or he walks or both. 90% chance that it rains or he walks. All right, the next big idea we need to have is independence. Suppose I flip a coin or I roll a die, and I roll a die at the same time. They're not going to talk to each other. One event doesn't influence the other. Whether the coin lands heads or tails, that doesn't tell me anything whatsoever about what number I'm going to roll on the die. This is a classic example of independent events. The outcome of one has no effect on the outcome of the other. Now, there are lots of things that are not independent. So like for instance, if I'm studying vehicles, I want to know the color and the type of a vehicle. Well, if you tell me what the vehicle type is, that's going to change the odds of what the color is. Turns out that people who buy minivans are more likely to choose white. It's a safer color. You've got a kid hauler or something like that. On the other hand, people who buy sports cars are more likely than average to buy black because it's cooler. So these are not independent. Telling you one thing tells you something else about the other thing. The type of vehicle tells you something about the color of the vehicle. So what do we do with probabilities and independent events? This is great. If the events are independent, then calculating the probability is nice and simple. All I have to do is multiply them. So, for instance, I flip a coin and I roll a die. I know the probability of rolling a 4 is 1/6. The probability of flipping heads is 1/2. So the probability that I will simultaneously both the coin will be heads and the die will roll a 4 is 1/2 times 1/6 is 1/12. There's a 1 in 12 chance that both will happen. Or if I just roll 2 dice and I would say, well, what's the chance that the first die is going to be a 2 and the second die is going to be a 4? Well, each one is a 1 in 6 chance. I multiply them out. 1/6 times 1/6 is 1/36. Now, what if I have multiple independent events? Suppose I take a coin and I flip it 5 times in a row. What would be the probability of getting all tails, every single one? Well, each one individually is a half, so I got to multiply all 5 of those 1/2s together. 1/2 times 1/2 times 1/2 times 1/2 times 1/2, also known as 1/2 to the power of 5, which is 0.03125. Only a 3% chance that that's going to happen. It's not very likely you're going to flip a coin 5 times and get 5 heads in a row or 5 tails in a row. But let me ask the question this way. Suppose we flip a coin 4 times, we get all tails, all 4 flips. Then what will be the probability that the 5th flip is tails? Most people want to, well, it can't be. It's less likely to be tails, right? Wrong. These are still independents. The coin doesn't have any memory. It doesn't remember what it did last time. The probability of any individual flip is still 1/2. No matter how many tails we get, the next one is still a 50-50 chance. Here's another example. There's another probability example. Let's consider there's a family. A family is going to have 2 kids. What will the probability that there will be 1 boy and 1 girl? Okay, the probability of boy is about a half, probability of girl is about a half. So they're independent events, right? So a probability of boy and a girl is a half times a half is 1/4, right? Wrong. This is wrong because there are 2 different ways this can happen. Either the boy is older and then the girl is younger, or the girl is older and the boy is younger. There are 2 different outcomes that consist of this event. This event of a boy and a girl has 2 different parts to it. 1 boy and 1 girl, or 1 girl and 1 boy. And each of those, there's a 1 in 4 chance that you get an older boy and a younger girl. There's a 1 in 4 chance of getting an older girl and a younger boy. Both of those 2 outcomes has a 1/4 probability. So, in actual fact, the chances that a family with 2 kids in it will have a boy and a girl is 1/2. 1/4 plus 1/4 is 1/2. Let's consider this one. What if I'm rolling dice in the game of Monopoly? All right, in the game of Monopoly, players roll 2 6-sided dice, then add up the total of the 2 dice, and then they move their player that number of spaces. So there are a total of 6 times 6 equals 36 total possible outcomes for the 2 dice. So you got 6 possible numbers on the first die, 6 numbers on the second die. Any number on the first die can be followed by any of the 6 numbers on the second die. We have 36 total outcomes. So how about this? What if I say, what's the probability of moving 8 spaces, of rolling an 8? Well, I need to count out the different outcomes. It turns out in this case, there are 5 different outcomes, 5 different ways to roll 2 dice to make an 8. For instance, the first die can be a 2 and the second one can be a 6. The first die can be a 3, the second one can be a 5. The first die can be a 4 and the second one can be a 4. the first die can be a 5 and the second one can be a 3. Notice that's different than first the 3 and then the 5, just like the boy and the girl example. Or the first die can be a 6 and the second die can be a 2, which is different than the 2 and the 6. So there are 5 different outcomes. Each one of these outcomes has a 1 in 36 chance. So if we add up all 5 of these 1 in 36 chances, the probability when you're playing Monopoly that you're going to roll an 8 is 5 out of 36. Now, what if we have non-independent events? Let's do some examples of that, because that comes up a lot too. Suppose I have a bag. The bag contains 20 little poker chip sorts of things, and they're different colors. Let's say 7 are red, 8 are blue, 5 are green. And I'm going to draw out 2 chips. I want to know, well, what's the probability that both of the chips I draw out will be blue? Well, the first one is pretty straightforward. There are 8 chips that are blue. There are 20 chips total. So the probability the first chip is going to be blue is 8 out of 20. So there's a 40% chance. But notice in this case, I'm going to draw out a chip and then I'm going to draw out another chip without sticking the first one back in there. So for the second draw, well, that's going to change. For the second draw, there are only 19 chips left in the bag. And I removed one of the blue ones, so only 7 of those 19 chips are now blue. So now for the second chip to also be blue, that's a 7 out of 19 chance. It matters what happens the first time. If I didn't draw out a blue one, well, then it would be different than that. So in this case, I need to consider how the first event affects the second event. So the first event, probability of first chip being blue is 8 out of 20. Probability of second chip being blue is 7 out of 19. And so those are the two probabilities I multiply together. I want the probability that the first one is blue and the second one is blue. Now I know what those probabilities are. I multiply those out. I get, 8 times 7 is 56. 20 times 19 is 380. So I have about a 15% chance of drawing out 2 blue chips. Let's do another example. Let's consider this problem. What percentage of non-truck SUV vehicles are white? All right, so I Googled a bunch of numbers. I found that 29% of all vehicles sold in North America are white. 69% of all vehicles sold in North America fit in the truck SUV category. And further, that 33% of all truck SUVs sold in North America are white. How do I use, so I got 3 pieces of information, and I got a question. Okay, so how do I use all that information to figure out what I want to know? All right, so this is kind of complicated. I think it's really useful. Problems like this, I think it's very helpful to organize our information into a table. We have basically all vehicles now will fit into one of 4 categories, okay? So we've categorized them as either truck SUVs or non-truck SUVs, and either white or non-white. So every vehicle fits into one of these 4 categories: a white truck SUV, a white non-truck SUV, a non-white truck SUV, or a non-white non-truck SUV. So what I do is I lay down a grid, a table just like this. And so I've got the first column is the trucks, the second column is the non-trucks, the third column is the total, add up everything. The first row are the white stuff, the second row is the non-white stuff, the third row is the total. So first I want to put all these informations in there. Notice that 29%, that is the 29% of all vehicles sold in North America. So that's going to go into the total column because that doesn't distinguish between the trucks and the non-trucks. So I put 29% at the end of the white row. Then it says, and I know that everything has to add up to 100%. So 100% minus 29% leaves me 71% vehicles being non-white. Similarly, that 69% applies to all vehicles. So that's going to go into my total row. 69% of all vehicles fit into the truck SUV category last year. So I put 69%. That's on my total for the truck column. And then, 100% minus 69% leaves, it must be 31% non-truck SUVs. So the first thing is I organize these totals. Whenever you look at a percentage, this is really important. Whenever you look at a percentage, think carefully about what does that percent apply to. That's a percent of what? So those first 2 numbers are percentages of all vehicles. So they tell me stuff that go into the total column and row. But the third thing, that's 33%, not of all vehicles. 33% of the truck SUVs sold in North America are white. That's a different sort of number. So let's consider this. What does that apply to? That applies to all the truck SUVs. And we know that that's 69% of all vehicles. So that means 33% of the 69% are white truck SUVs. So what we of means we multiply 33% of 69%, so we do 0.33 times 0.69, and we get 0.2277 or 22.77% of all vehicles are white truck SUVs. Now I can start filling in the middle of this table because those four entries in the middle should all add up to 100%. The rows add up and the columns add up and then everything adds up to 100%. So now I know one of my four categories. I know one of my four categories is 22.77% of all vehicles is a white truck SUV, or are a white truck SUV. There we go. So now I know that in total, all vehicles sold in North America, 29% are white. So I can now subtract. I can say, well, 29% of all vehicles are white. 22.77% of all vehicles are white truck SUVs. So I do 29% minus 22.77% leaves 6.23% of all vehicles are white non-truck SUVs. So, and then I could subtract now and I could figure out the percentage of non-white trucks and then the non-white non-trucks and all that sort of thing. But that's not what I want in this case. My question was, what percent of non-truck SUVs are right? Again, whenever there's a percentage, think very, very, very carefully about what does this percentage apply to? So in this case, we've got 6.23% of all vehicles are white trucks SUVs. A total of 31% of all vehicles are non-truck SUVs. So we do the 6.23 divided by the 31%, we get 0.201. 20.1% of all non-truck SUVs are white. All right, so let's summarize what we've talked about. First of all, probability. That's a number in the range from 0 to 1, where 0 means it's not going to happen, 1 means it's guaranteed to happen, and then the different decimals and fractions in between tell us the likelihood of the event. Mutually exclusive are events that cannot both happen. Either this happens or that happens, but never both. The addition rule allows us to calculate the probability that either A happens or B happens or both. All that keeps me happy. And so in order to do that, I add up the probability of the first event plus the probability of the second event minus the probability that they both happen simultaneously, because that's included in both of those two numbers, and I only want to count it up once. Independent events are events where the first thing has no effect at all upon one another. That's like rolling dice, flipping coins. Those are classic examples of that. And if I have independent events, shoot, the probability that this and that happen, that both A and B happen simultaneously, is you just multiply the two probabilities together. That's great. That's wonderful. That's easy. If they're not independent, then we got to think harder. It's always important to think carefully about how an event may contain several different outcomes. So in order, if that's the case, then I need to add up to get the probability of the event, I need to add up all the different outcomes. So we need to think carefully about that. And the hard cases are the non-independent events, where knowing the result of one event changes the probability of the other event. And those tables where I add up, if everything has to add up to 100%, where I can put things into four categories based on these different characteristics, that can be a really useful tool to do that. And that's an introduction to probability.